In this video, we will be talking about collisions and the law of conservation of momentum. So both of those combine pretty well together. But of course, in order to talk about collisions, we need to talk. I just had a brain fart there. In order to talk about collisions, we need to talk about the types of collisions. So what are the types of collisions? Well, we have three main types of collisions. We have elastic, inelastic, and perfectly inelastic. So let's write down the details for an elastic collision. So an elastic collision conserves kinetic energy, and the objects sort of bounce off each other. Not like a basketball bounce, but it could also be just when they collide, they knock away. So sort of like a pool ball. Even the pool balls aren't rubbery or bouncy, they still bounce off each other. They kind of click and then go in the opposite direction. Okay, how about for an inelastic collision? Well, an inelastic collision doesn't conserve kinetic energy, which you're kind of scratching your head. You're probably wondering, well, what about the law of conservation of energy? Okay, well, you might lose some of this energy in deformation of some metal of the objects colliding, or you might lose some of the energy as friction. That's where it goes. It doesn't. You don't just lose energy in the entire universe. Okay, it just doesn't conserve energy within the two objects or three objects that collided. But an inelastic collision also has some deforming. So sort of like an example, a real world car crash. The cars will deform, and they'll kind of mold together some parts. Some of the parts will fly off, some of the metal pieces will fly, some of the glass will fly off, and which is actually what you lose a lot of momentum for. If that didn't happen, the collision would be a lot more dangerous. Everyone would die in like even lower speed car accidents because a lot of momentum is lost from objects flying away. But that's besides the point. How about perfectly inelastic? What is sort of the difference here? Well, for perfectly inelastic collisions, you have a maximum loss of kinetic energy. That doesn't mean your kinetic energy goes down to zero. However, compared to inelastic collisions, maybe you lose some kinetic energy in friction, right? But for perfectly inelastic, you lose as much kinetic energy from friction or deformation as possible. You lose as much as you possibly can. And also for perfectly inelastic collisions, the objects also completely stick together. So let's say a bullet hitting a wooden block. Well, the bullet kind of lodges into the wooden block, and then they're now a combined mass. It's basically together. So perfectly inelastic collisions, things completely stick together compared to inelastic. Now you might be wondering, where's the perfectly inelastic collision? Perfectly inelastic collision never really happens in real life. Sort of perfectly inelastic. Perfectly elastic never happens. There's no such thing as really perfect in our universe, but perfectly inelastic really has the same properties as elastic if you want to be super technical. But what is a huge similarity between all of these, and how does this tie into momentum? All of these conserves momentum. Not momentum. I just shortened it because I ran out of space. But in order to calculate things with all of these, instead of using energy, like kinetic energy or potential energy, where a lot of it's lost unknowingly to a certain amount of friction, you can use momentum. So momentum is a good tool that's always conserved in collisions. Now that you know all of these, we can talk about the law of conservation of momentum, but in order to do that, I'm going to show you problems. I think that's the best. I think that's probably going to be the best way to show you how to interpret the law of conservation of momentum. But that's enough yapping for now for me. Let's go and do some problems. I just came back from the swimming pool. My skin is burning from all the chlorine, and I just ate Burger King. I know. I'm a big bag for that. I know. But let's do this problem. Let's see. Okay, so we have a red car with a mass of 1,000 kilos. So car, always write down the information as you're reading it, so you don't have to write it down later. So you know, and you also know what you have. And you also have a blue car that is traveling, that has a mass of 1,200 kilos. And let's look at all the information we have now. Well, we have the initial speed traveling east of the red car. So the red car is traveling east at 25 meters per second, and the blue car is headed at an angle, sort of. But let's see what we need to solve. Well, we need to solve that the cars collide together, moving off of the same final velocity, and we need to solve for their final velocity and the final momentum after the collision. So in the problem, it states that the cars collide and stick together and move off of the same final velocity. So the largest hint here is stick together, and this tells us already that we have a perfectly inelastic collision. And these are honestly the easiest to solve for out of all of them. Elastic collisions, they still aren't that bad, but perfectly inelastic, there's actually not that many steps. You don't even need to understand the steps. You can just memorize it if you want. I don't recommend that. But let's see what's happening in this problem. So we have a red car heading directly east. So let's draw out its path. So the red car is heading directly east, which is to the right. I'm pretty sure in my previous video I said that east was traveling to the left. Yeah, I had no idea what I was talking about. I should have used never eat soggy waffles. I don't know if you guys have heard of that acronym or not. But this red car is traveling east with 25 meters per second. Okay, that's an important detail. Note it down. And we have our blue car traveling 30 degrees south of west. So if we were to draw sort of a line here, we have a blue car traveling 30 degrees south of west. So 30 degrees south of west is sort of like drawing an arrow, and we pull this arrow pointing to the west 30 degrees to the south. So the true path of this car is like so. And if you were to try to draw an imaginary line here, this is the lines facing west. The problem stated that it was traveling 30 degrees facing west, 30 degrees south of west, correct? But due to, I think it was interior transverse angles, this is also 30 degrees down here. So the angle between their two roads is also 30 degrees, and the blue car is traveling at 30 meters per second. So now that we have these two, we need to write down the velocity vectors. Due to the fact that this problem is in 2 dimensions, we need to write down all the components of the velocity vector. So what is the velocity of the red car? Well, the red car is traveling to the right at 25 meters per second. So the velocity of this red car is 25 meters per second in the x component, but since this car isn't moving in anywhere in the y direction, it's 0 meters per second in the y component of the velocity vector. Okay, how about this blue car? Well, the blue car is going to be a little more sophisticated, but we can kind of represent this like a triangle. So if we were to draw a triangle like so, and this is where the blue car is, we know that the blue car is traveling at 30 meters per second, correct? Well, we can sort of treat the speed like a triangle, and we can find the components of this vector individually. So let's find the components of this vector individually if this is at 30 degrees. Well, if we know that the hypotenuse of this triangle is 30 degrees, and we know one of the angles, we can take the sine of 30, and we can also take the cosine of 30 to find the adjacent side length. So the cosine of 30 solves for this, and the sine of 30 solves for the y component of this triangle here, to solve for the components of the vector. Now that we have this, we can evaluate all of the sine and the cosine, the trig stuff, to get 25.98 meters per second for the x component of your blue car, and 15 meters per second for the y component of your blue car's velocity. Now keep in mind that negatives and positives matter, so due to the fact that this blue car is traveling downwards and to the left, usually in coordinate systems, the downward and to the left vector looks like so. Therefore, both of the components will be negative. So both of the components of our blue car's velocity will be negative. So let's write that down. So negative 25.98 meters per second, and also negative 15 meters per second is the velocity for the blue car. Now that we have the two velocities, we can add their momentums together. So how do you calculate their momentums? Well, we can calculate the red car's momentum by multiplying the mass of the red car by its velocity vector. And we can also calculate the blue car's momentum by multiplying the blue car's mass by its velocity vector. So if we solve for both of these equations, we get that the red car's momentum is 25,000 in the x component and 0 in the y component. And we also get that the x component is negative 31,176. And the y component is negative 18,000 for the momentums of both the cars. Now I had to move these up because I was running out of space. But what can we do? Well, we can solve for the initial momentum of the system. Well, the initial momentum should be equal, so P initial should be equal to the final momentum because momentum is conserved in all collisions. So let's go ahead and try to see how we can find the initial momentum. Take a guess, and I'll show you guys. Well, you can actually solve for the initial momentum by adding the two momentum vectors together. So if we add these two vectors together, we get something that looks like this. And then now that I've added these two vectors together, so this comes from here. Let's use different colors actually. Let's use green. This comes from the red car's momentum, and this comes from the blue car's momentum. So if we add them together, the vector is negative 6,176 and negative 18,000 as the total initial momentum. But since in all collisions momentum is conserved, we should expect that the final momentum looks like this as well. So the final momentum after these two cars collide at the intersection here, this is the X point, this is where they collide. So the final momentum should equal negative 6,176 and negative 18,000. So now that we have our final momentum due to the initial momentum before the collision, well, we can solve for the final velocity. So we already solved for the final momentum, as the final momentum is equal to the initial momentum. And we solved for the initial momentum by adding the two momentums of the red car and the blue car together. Now that we added those two to get the initial momentum is always equal to the final momentum. So we have solved for, let's use orange, the momentum in this problem. I think I just repeated myself like 10 different ways and then said the same exact thing. Okay, I'll stop dilly-dallying here. Let's solve for the final velocity. Well, we can solve for velocity as momentum is equal to mass times velocity. We can solve for the velocity by dividing mass from the momentum. So if we divide the mass of the cars, we can find the momentum. Well, here's a trick question. Not really a trick question. Here's a conceptual question. What's the mass of the cars after the collision? Well, due to the fact that the cars actually fully stick together, they're 1,200 kilos all combined together add up to 2,200 kilos. So the total mass after the collisions of the two cars is 2,200 kilos, assuming it's a perfectly inelastic collision. Now that we have the final mass, of after the collision, and we have the final momentum, we can solve for the final velocity. So all we have to do is need to divide the velocity by the mass of the two cars together. And I need to make certain I find more space. So let me try to pause the video and do that. Okay, so I had to erase all the equations I had on the side here to find space. I couldn't move anything around, but in order to get more space. But all I did here was divide our final momentum or initial momentum, both of them are the same thing, by the final mass. So the final mass of the cars were just the cars added together due to the fact that they fully perfectly stuck together. And then if you divide these two things, you should get a vector value of negative 2.81 meters per second in the x component for your final velocity and negative 8.18 meters per second. Now if you calculated the initial kinetic energies of the cars individually and added them together, and you try to solve for the final kinetic energy of the cars and added them together, it would be significantly lower. But let's try to draw out so the velocity of the cars is, I need to find a great color, orange. Okay, so the cars will probably go in a direction, so it's kind of go in this direction here, and some direction that looks like this. So these two cars collide, then the cars will kind of go in the direction of the orange arrow, assuming it's a perfectly inelastic collision. Now this problem, it mentions a billiard ball, a very common sight in Rainbow Six Siege, by the way. If you want to play with me, hit me up. I'm top 1000 champ. Hit me up if you're also top 1000, or if you're diamond or some shit. But why am I programming myself? What the fuck? Okay, we have a billiard ball. You're most of the time it's going to be an elastic collision. So elastic. But the law of conservation of momentum always still holds true. So it doesn't even matter what type of collision happens. Your initial momentum is always going to be equal to your final momentum. And the only way you can tell if it's elastic or inelastic or not, or perfectly inelastic, is just either from the problem's directions or when you solve for the kinetic energy afterwards. After you solve for everything. Genuinely doesn't matter. You don't even need to use kinetic energy. You just need to know that the final momentum is equal to the initial momentum and vice versa. So we have a billiards ball labeled 1. Boom. 1. Moving horizontally and strikes another billiards ball. So let's say it's moving to the right. And it strikes a billiards ball labeled 2 at rest. So this is still. Before the impact, ball 1 was moving at a speed of 3 meters per second. So let's write that down. And after impact, it's moving at 5 meters per second. So this is before. And then this is after. So we have our ball 2 moving in a mysterious direction. We don't know. But we know that ball 1 is going. Okay, let's move ball 2 so we have more space. Ball 1 is going at a 50-degree angle. 50-degree angle from the horizontal. So it moves 50 degrees upwards from the original direction at 0.5 meters per second. If the two balls have equal masses of 300 grams, so m is equal to 0.3 kilos. What is the velocity of ball 2 after the impact? So remember, we need to find the initial momentum and in order to find the final momentum of this system. So the initial momentum already given. Well, ball 2's initial momentum is just 0 kilogram meters per second. But ball 1's initial momentum is different. So we just need to multiply the mass by the velocity. And then once you multiply the mass of ball 1 by its velocity, and as I wrote here, I wrote it in as a vector. And I wrote it with positive 3 because the ball is traveling to the right. And also 0 in the y component of this velocity vector because this ball isn't moving up or down. It's only moving horizontally. So if you multiply these together, you should get a initial momentum of 0.90, 0 kilogram meters per second. So this is equal to your initial momentum. So now that you have your initial momentum, well, you have your final momentum due to the law of conservation of momentum. But in order to solve for the trajectory or the momentum of ball 2, we need to solve for the momentum of ball 1. That's the only information we have. But we know that ball 1 is traveling at 0.5 meters per second and at 50-degree angle from the horizontal. This is actually not a 50-degree angle. This is more of like a 30-degree angle, but just imagine that it's not drawn to scale, let's say that. So in order to solve for the components of this, we need to multiply our speed of ball 1 by the sine and cosines of the angle 50. So these are the components of your, this is the y and this is the x component of your final velocity of ball 1. And if we were to write this down in a vector form, so v of f ball 1, we write it like so. So we have 0.32 and 0.38 meters per second. And again, these are positive because it's traveling to the right and upwards. And to the right and upwards, if you draw a vector that's pointing to the right and upwards, it's in the first quadrant, which means that both x and y components are positive. So we have the velocity of your ball 1. Now we need to find the momentum of ball 1 in order to find the momentum of ball 2. Because if we add the two momentums together, so if we add the momentum of ball 1 plus the momentum of ball 2, we should get your initial momentum, or also your final momentum. So we just need to find your momentum of ball 1. Now that we have the momentum of ball 1 written here, we can solve for the momentum of ball 2. So remember what I said, the momentum of ball 1 plus the momentum of ball 2 should be equal to your final momentum, or also your initial momentum. So we just need to modify this equation. Well, if we modify this equation a little bit, we have, so this right here is good, this right here is good, but we don't have the momentum of ball 2. That's what we're trying to solve for. So we can actually subtract the final momentum with the momentum of ball 1 to get the momentum of ball 2. So we can actually subtract these. So as I set up this equation, it'll look like so. And if you have, or once you evaluate this equation, but let me make this more clear. This is your initial momentum that we calculated, and this is the momentum of ball 1. Let's change the color. This is the momentum of ball 1. The final momentum of ball 1 after it strays from its path. So once you subtract these two vectors, you should get a new vector. And this new vector written down here, let's use this orange. This new vector represents the momentum of ball 2. So this sort of goes in this direction here, which is already what I've drawn. Now that we have this momentum, we can divide our momentum again. We can divide, oh my god, we're running out of space. I'll just erase everything. But we can divide our momentum by mass to get velocity. So before I erase everything, just take a quick look if you want to look at the work again. I think the pathing I did the work was from up to down on the left side, and then from up to down on the right side. So this is like the steps in order from 1, 2, 3, 4, and then 5, and then 6 here. Okay, I'm gonna erase it now. And since we have our final momentum of ball 2, we can divide it by the mass. So we can divide the mass of the ball, which is 0.3 kilos, and then your final velocity is equal to 2.68 and negative 0.383 meters per second via each component. So this is the x component, this is the y component of your velocity vector of your ball 2 after an elastic collision. So this is less of a collisions problem. This is more of a spontaneous explosion problem. So let me try to explain something. If you have, let's try to explain this intuitively at least. If you have, let's say, a ball, let's say a basketball, and it can only explode into 2 pieces, well, they better explode, if the explosion happens directly from the center of the ball, well, they better explode into 2 pieces in opposite directions. And also, in this case, if a meteorite explodes, let's say there's a meteorite, it explodes, well, the pieces better go at least similarly in kind of a triangle, like so. But if some velocities are faster than the others, then there might be more movement in this direction and less movement in this direction. And that's kind of the intuition that's going on in this momentum problem. If this rock explodes in deep space, well, the directions that the other rocks go better make sense. It's like this. If the rock explodes directly from the center, it wouldn't make sense if all the pieces went in one direction. There should be maybe a little bit of piece back here that at least goes in the opposite direction if the explosion happened directly from the center. But it wouldn't make sense if all the pieces went in one direction. That's kind of intuitively what's going on here. But let's see if I can. Let's work on this problem and stop yapping. Okay. So you have a 200 kilo rocket deep in space, moves with the velocity of 121 meters per second in the x component direction and 38 meters per second in the y component direction. So J just stands for y, I stands for x. If you get further on to physics, K will be there, and K stands for the z component. So it suddenly explodes into 3 pieces, first being 78 kilos, moving at this guy, and second piece 56 kilos moving at this guy. So let's find the initial momentum in order to solve for the final momentum, or the final combined momentum of all the 3 pieces. So in order to solve for the initial momentum, I need to multiply the mass of the rocket by its velocity. So this right here is the initial momentum. So all I did was multiply the mass by the velocity here. So now that we have the initial momentum, we just need to calculate the momentums of all the rocks. So let's represent the momentum of rock 1 by P1, the momentum of rock 2 by P2, the momentum of rock 3, currently the thing we're trying to solve for, find the velocity of the third piece, unknown. And this should equal the initial momentum of our system. So in order to solve for momentum of rock 3, in order to solve to find the velocity, we need to find this guy and this guy. We already have initial momentum here, but we don't have the momentums of rock 1 and 2, and we can actually solve for that because we are given the masses and the velocities of each of those rocks. Let's go ahead and try to solve for them. So I did all the work for you guys. I wrote it all down. I don't think that. Actually, let me know what do you guys think of that. I've been messing around a little bit with like the pausing mechanism, so you guys don't have to watch me write down the entire thing. I think it's unnecessary. You guys already know that I'm multiplying mass by velocity here, so there's no point in you watching me do all this. And this part is just typing it into a calculator. So if you guys like that, that I'm pausing it and then not reading through the entire thing or writing down and wasting your time, put that down in the comment section. Let me know. Actually, truly give me some feedback for these videos. I actually like that. But this is our initial, momentum for our first rock. So we got the 78 kilos here, multiplied by its velocity, and we also got the second rock's momentum, 56 kilos, multiplied by its velocity. And if you're confused on why I wrote negative 88 for the y component of the velocity, it's because there's a negative sign here. Either the negative sign at the beginning of the rock 1's velocity is more clear, the negative sign here is a little bit harder to spot. So this negative actually matters. Or that minus symbol actually matters. So we have our velocities, our momentums of rocks 1 and 2. Now that we have those, we can actually rewrite the equation, this equation, to go like this. Actually, let me move this to the side. We can rewrite this equation. To look like this. So initial momentum minus the momentum of rock 1 minus the momentum of rock 2 in order to get the momentum of rock 3. So just a little bit of algebra. I just manipulated this and I subtracted P1 and P2 onto the right side of the equation. So now that we have this formula right here, and we have our initial momentum, we have our first and second rock's momentum, so we can solve for the momentum of rock 3. So let me set up the formula and write it all down here. So this equation right here is the same as this one right here. And I just underlined the vectors for the momentums according to the colors I boxed them in, just to make it more clear. So the orange underline is the same as the orange box, the green underline same as the green box, blue underline same as the blue box here. But once you subtract all these vectors, you should get a momentum, the momentum of your third rock. So let's subtract all these. Wait, before I do that, I just noticed something when I was doing my calculations. This should be a minus here, by the way. I messed up the minus there. The rest of the minuses are fine. Okay, now we can solve for this. So once we subtracted all of these vectors, we should get our momentum of our third rock, which is this guy right here. And let's make it red. Let's assign it with the color red. Now that we have momentum, we can divide the momentum by mass. So we can divide our momentum by mass to get its velocity. And that's what the problem is asking us to solve, the velocity here. So in order to get the mass of rock 3, all I did was subtract the big rock's mass with the rocks 1 and 2's masses. So once you subtract all of these, you should get a mass of the rock 3, which is 66 kilos. I'm not going to write the units because I'm not going to lie, this momentum unit takes up a lot of space. But once you solve for this simple equation, you should get the answer 732.45 meters per second for the x component and negative 79.64 for the y component of your velocity of rock 3. So, as always, I got these questions off of OpenStax. If you want to check it out, it's an online textbook. Link is in the description. And if you have any questions, put it down in the comment section. I hope this video